Hello everybody. I'm here with the Van de Graaff generator again, and what I'd like to show you today is that the distinction between insulators and conductors, it can really start to break down when we put ourselves in situations where there's very, very large charges. The Van de Graaff generator we've seen before generates large charges. I actually don't know whether this one makes a positive or a negative charge. I'm going to assume it's positive. But between me and it is a lot of air. And air is usually a pretty good insulator. If you have bare wires running through the air, as long as no one touches them, electricity is probably not going to jump out of them. But of course, as we see with lightning, and this thing will produce lightning, air can break down and allow electricity to move. So why does this happen? Well, just like we saw a mass warps the space around it and creates what we call a gravitational field and allows objects to start to move from areas of different potential energy. So like a book falling from high up or a rock falling from off a cliff, a lot of energy results in that transfer. The charge warps the space around it and creates what's called an electric field. And large amounts of energy can transfer in an electric field as well. If the electric field gets large enough in a certain location, no insulator can actually overcome the energy that would be released if charge jumped, and insulators will start to break down. What actually happens to the air between me and the Van de Graaff generator? It actually becomes ionized. So the O2 molecules get ripped apart into O3 molecules, and O3, which we call ozone, actually has a charge on it, and then those O3 molecules can carry the electricity from one place to another. So essentially, assuming this is positive, and the opposite arguments would be true if this was negative, the wand is wired to the Van de Graaff generator. The Van de Graaff generator, its green base and the wand are wired to the earth through this pin, which we call the ground pin. And because the earth has a lot of electrons, when this ball gets too high a charge, it will start to steal them through the earth, either from its base or from this wand. And we'll see a lightning bolt. So when I have it relatively close, it makes lightning bolts fairly quickly, and they're not too big. The farther I go away, the less likely it is to happen, but when they happen, they're rather large. You can steal this from any nearby source of electrons, and I take the wand away. It'll start to take it from its own base, which is also wired to the earth. It's also perfectly capable of taking electrons from me. Ow. I don't know if you could see that bolt from my hand. It's not taking a huge amount of electrons, and that's why it's relatively safe for me to do this. Although it's rather violently taking those electrons away from it, it's only taking a small number, and that means I don't get hurt too badly. You obviously can't smell what this room smells like right now, but I can smell ozone. Ozone has a very clear smell. Kind of smells like a photocopier room, which uses highly charged objects, or like the air right before a thunderstorm. You get kind of this burnt, weird smelling thing. Sometimes blenders will smell like it, sometimes model train sets will smell like it. It happens around electrical engines a lot. It's not good to breathe too much of it, which is why photocopiers and laser printers really shouldn't be in small rooms. But anyway, we just watched air break down due to the large electric field.